So welcome back to the third and last AMS Colloquium by Camillo De Lellis. Most of you have probably attended the first two talks, but maybe some of you did not attend. I am just going to say briefly that Camillo is a permanent professor at the Institute of Advanced Study. He received many awards, including the Fermat Prize. He's in the field of partial differential equation, geometric measure theory, and other topics. So he will continue his talk on flow of non-smooth vector field.
Thank you very much, Wilfried, and thank you to the aficionados for coming to listen to the third lecture. So like I did for the second, I'm going to give a small recap of what I said in the first and second lecture, even though this should be an independent one, which I'm reasonably confident that it's possible to understand without having been at the first two. Okay, so we're concerned with the flow of a vector field U. So as usual, what we have in mind is to look at trajectories in the Euclidean space or in an ambient manifold whose tangents are a prescribed vector field which is depending on time and space. And we bundle the trajectories together in a map which depends on time and space, which, I mean, in the slide is called phi, through the prescription that the value of phi at the point dx is given by where the trajectory lands if it started at point x at time t equals 0. So this is what we know for a smooth vector field or C1 vector field from standard calculus. And what we're interested in is to understand how far we can push the regularity of the vector field and still have a meaningful notion for a solution of this system of ordinary differential equations. Okay, so the flow of the vector field is naturally connected to two partial differential equations. So one of them is the transport equation, which you see in red over there. And when you're smooth, you solve the transport equation even if and only if you are actually constant along the trajectories which are given by the flow. It's a very simple computation. And then there is another equation which is connected to it, which is called continuity equation, which is the second equation in red over there. And that is a bit more complicated through Liouville's theorem. It's, so this density rho is just the push forward through the flow of what was the initial density at time t equals 0. And you might notice that if you are a divergence-free vector field, the two equations are really the same. Okay. So now, in general, we are going to look at vector fields which are just summable, but we are going to assume that the divergence of U is bounded. In particular, because that, in the classical setting, would give us a uniform bound on how much the flow is compressing or dilating sets. Notice that if divergence of U is equal to 0 and you have a classical vector field, then the flow phi is actually measure preserving. So we're like trying to understand a low regularity situation, but in a situation in which we have a control on the divergence, which would tell us that the flow phi is not able to concentrate large sets in small sets. Okay, so solutions of the PDEs are going to be understood distributionally. So this means I can multiply, say, the function U times rho, for instance, because there is enough summability to make sense of that product as a summable function. And likewise, divergence of U is actually a bounded function, so I can multiply by rho. And instead, trajectories of the ODEs, when you're not smooth, are understood collectively, really as a flow phi. So I'm not looking at the trajectories alone, like, you know, as isolated objects. And besides the obvious requirement that this regular Lagrangian flow phi, which is only a measurable map, gives you for almost every x a trajectory which is absolutely continuous and which is solving the ordinary differential equation at almost every time, you have the prescription that the push forward of the Lebesgue measure of this through this flow is actually bounded. Okay, so this is something which we call Liouville's axiom. And in a context in which U is smooth, this would actually be a theorem because you would be able to relate that constant C of t to the size of the absolute value of the divergence of U. Okay, so in the first lecture, I presented the Di-Perna-Lyons theory. So there is a soft part which relates the well-postness of the two equations to the well-postness of the regular Lagrangian flow, and it essentially tells you that the two are kind of equivalent. So well-postness of the ODE, of the regular Lagrangian flow, implies the well-postness of the PDE, but surprisingly also the vice versa, which is one of the in a sense, is one of the starting point of the Di-Perna-Lyons theory. There's a soft part number 2, which is that the well-postness of the transport and continuity equation is in fact implied by something which is called the renormalization property. So this is an obvious property for solution of the transport equation for smooth vector fields, since they are constant along the trajectory of the flows. If rho is a solution, then rho squared is also constant along the trajectory of the flow, and then it is a solution. But when you are in a low regularity setting, this is not at all an obvious thing. In fact, we saw in the last lecture that it might fail. And so this, we actually give a definition if the solution of this property, and it's called the renormalization property. And the hard part of the Di-Perna-Lyons theory is that if your derivative, so if you have a vector field and your derivative is Lipschitz, of course, you have the classical theory of Cauchy-Lipschitz, which tells you that everything is nice. But if you're just a little bit below Lipschitz, so you just have a summable derivative, so you are in the Sobolev space, or in the case that your derivative is a Radon measure, so the case of functions of bounded variation, which was covered much later by Ambrosio, and you have certain summability conditions on the density rho, then you actually have this renormalization property of soft part 2. And when you have this renormalization property, then you have well-postness for all these objects. So for sufficiently summable solutions of the transport equation, for sufficiently summable solution of the continuity equation, and for regular Lagrangian flows. OK, I also told you that it's actually possible to give kind of a priori estimates on the regular Lagrangian flow, which is showing you that even though it's a measurable map to start with, in fact, it's Lipschitz outside of a set of small measures. So it seems to gain almost one derivative. But for other purposes, when you actually try to measure what is the derivative gain of this object, it's actually more kind of a logarithmic gain. And this answered to a like generalization of a conjecture of Bressan, which in the original formulation is still open, and which I presented in the first lecture. OK, so I'm not going to give you a summary of the second lecture. So on the second lecture, we considered several possible questions and directions in which you could stretch the theory. And I essentially showed you by citing several recent results that the theory, even though it seems to be kind of wanting in several places, is in fact optimal. So if you lower the regularity of the vector field a little bit, everything breaks down. You can't give up this Liouville axiom and actually hope that it is a theorem. And you can't give up the summability of the solutions of the transport and continuity equations, which gives you the well-postness, even though you can make sense of the equation for less summable solutions. OK, so in yesterday, one of the constructions, so one of the key constructions which showed that you cannot hope for a Di-Perna-Lyons theory for something which is less regular than a Sobolev vector field was presented by me in detail, and it was based on this construction of Depot, which I want to go through again today because it's going to serve my purposes for what I want to tell you. OK, so this is the idea of Depot in 2003. It recovered a much older result by Eisenman, which showed that if you're just looking at a summable vector field, which is divergence-free, having well-postness for the continuity and transport equation without some further information about the regularity of your vector field is actually not possible. OK, so this is a very basic vector field that you see depicted over there. So I just pictured 5 squares. But you have to imagine that this pattern is repeated in the two-dimensional space periodically. So you have this checkerboard, which is filled. And the center of the squares are all points in the integral lattice. The vertices of the squares are all half integers. The coordinates are all half integers. And half of the squares, let's say the white squares of the checkerboard, are actually left completely alone. So the vector field is identically equal to 0 there. And in the other half of the square, you have this counterclockwise rotation. So it's a vector field which has the following property. So it's piecewise linear, in fact. It has discontinuities, so it's not a smooth vector field, but it has pretty controlled discontinuities. And all the effect that this vector field has, for our purposes, is that if you flow inside one of these squares, this vector field for a certain time, and by convention I'm going to take that the time is equal to 1/2. Of course, I can kind of decide the time by simply varying a constant multiplication of this vector field, which would like vary the intensity. And so at time t equal 1/2, if you apply a flow of this vector field, what it does, it turns whatever is inside one of these squares where it acts, everything by 90 degrees counterclockwise. Okay. So now I want to feed the transport equation with this vector field with an initial data. And initial data, it's also like something discontinuous, but something discontinuous in a very controlled way. So the initial data takes values 1 and -1 on dyadic squares. Now this time, these are dyadic squares whose vertices are actually points with coordinates which are integers. So the vertices are in the integer lattice. So, and again, the values are taking 1 and -1 with a checkerboard fashion. So half of the squares, you call them white, as if you were playing chess. The other half you call black, and then you put 1 and -1 constant values on white and black. OK, so here is what we want to do. We want to transport this initial value, rho in, with the flow of the pose vector field to get the function rho. And I'm just going to do this between the time interval 0 to 1/2. Remember that at time 1/2, I have rotated all of the squares of the previous checkerboard by 90 degrees. But now, pay attention that the checkerboard, which was devised to construct the pole vector field, is shifted with respect to the checkerboard that you start with by 1/2, right? So you see the picture over there on your left. So, I mean, the squares where the vector field is acting, they all contain 1/4 of the squares, I mean, like 4 little squares, which are each 1/4 of the squares over which the initial data is constant. And so when you wait time t equal 1/2, you will have rotated and exchanged the position of these 4 smaller squares, and the result is the checkerboard pattern that you see actually on the right. So you just get, again, the initial data, but you get the initial data where the frequency of change of the value between 1 and -1 has increased by 2. So you just get exactly the same pattern, but the squares of the checkerboard has become half of the side length as the previous checkerboard. OK, so now what do I want to do? I actually want to repeat this construction. So how do I repeat this construction? Well, at the next step, say between time 1/2 and 3/4, I just replicate the same vector field that I had at the beginning, but I shrink the domain by a factor 1/2, and I shrink also the intensity of the vector field by a factor 1/2. And now it actually takes just 1/4 time to like turn my little square, because the little square is smaller. So now I do that, and I feed the new checkerboard, so the like function that I had at time t equal 1/2. And at time 3/4, what I find is I find yet another refinement of my board. So now my board actually, my function which has been transported has actually frequency 4 times as the function that I had before. OK, and I keep doing this. I keep doing this at dyadic scales, and so each time this row that I get closer and closer to the time t equal 1 is going to oscillate between the value 1 and -1 on a checkerboard which is becoming finer and finer. So that's what happens in formulas. And in particular, what it happens is that rho at times t converges to an homogenization of rho at times 1, right? So it converges to an homogenization which has the value identically equal to 0. So it oscillates more and more, and it converges in a weak sense to a function which is identically equal to 0 because the values 1 and minus 1 average out on every particular region that you're looking at. OK, so now the idea of the pole was the following. So you can actually reverse the time to produce a solution which starts at time, say, t equals 0 as 0. And instead of coming from the larger checkerboard to the finer ones, you just think that you actually are going from the infinitesimal checkerboard and you're creating the pattern in a reverse fashion. And so now you've got a solution of your transport equation for that particular vector field, which at time t equals 0 was identically equal to 0, but as time actually progresses, becomes bigger and bigger, right? So I mean, it's in particular non-trivial. Now, since the identity, since the solution which is identically equal to 0 is also a solution, you see that by reversing the time in this process, you actually found an example of 2 different solutions for the same initial data for the transport equation. You might wonder how regular is this vector field, and I mean in a precise sense, in the sense of fractional Sobolev space, it actually has a fraction of a derivative for every fraction less than 1. So it almost has 1 derivative. In fact, it fails to be a vector field of bounded variation by very little. OK. So now, at this point, you could actually ask the following question. So, and this is what I left you with yesterday. So, of course, you could just advocate simply the following. If I'm following the pole on, from the procedure in which it starts with a large checkerboard and it keeps refining, well, as long as I stay for t less than 1, that is actually really the unique solution of the transport equation. Well, you can try to prove it by hands because even though there are discontinuities, it's actually a nice vector field. But you could also use the Di-Perna-Lyons and Ambrosio theory because it's a vector field of bounded variation as long as you stay far away from 1. So there's a unique solution, and then you converge to something which is homogenized, and from there on, the function is 0, and you can, continue it as 0. Now, you reverse the pattern, but if you reverse the pattern, actually, you have a starting time where the function is equal to 0, and you could just tell me that, it's much more reasonable to just say that the solution has to stay equal to 0. For instance, you could just say, I want to impose on my solution that it has the maximum principle, as it happens for solution of smooth equations, of smooth transport equations. So this is good. This is valid. I mean, you can, of course, in this particular situation, decide whatever you think it's a better solution between the two. But if you want to construct a coherent theory in which you have some selection mechanism which is going to produce a unique solution among maybe many, for every vector field u, which is not too smooth, you also want this selection mechanism to enjoy some stability. So you could ask a question like, maybe if I approximate suitably my transport equation by a smoothing mechanism, maybe the solution of the smoothed equations actually they're converging to a unique object. And so the first question that you could ask is that whether that is correct. And there's various ways that you can use to smooth your function u. Some of them are pretty precise. For instance, you could smooth it by making a convolution with a standard kernel. But you could also just say, more in general, let me assume that I pick up a regularization which keeps uniform estimates in whatever space you're interested in solving this problem. So for instance, say your vector field is not Lipschitz, but it's Hölder. Well, then keep uniform estimates on the Hölder norm. OK, and here I'm always assuming that the divergence of u is equal to 0, or anyway, it's bounded. And let's assume that the regularization that you pick is smart enough so that if you have a condition like divergence of u equal to 0, you're actually keeping it. OK, and I told you that in the last lecture that the answer is no. So the first triple of people to consider this and to prove a theorem about it are Ciampa, Crippa, and Spirito in 2020. And they just showed that the answer is negative if you just have LP divergence vector fields with a sufficiently small p. I'm not going to say more about this because a year later, in a paper with Vikram Giri, we have proved that the answer is negative for essentially the same kind of regularity class that you have for deposed vector field. So if you can have almost one full derivative, and this selection by smoothing would anyway be wrong. And if you are in 2 dimension, you have to take a time-dependent vector field. That is not so surprising, because if you are divergence-free and time-independent, then you are in a Hamiltonian vector field, and the problem kind of becomes 2D. Because if you have a smooth Hamiltonian vector field, which is time-independent in 2D, then essentially the trajectories, well, I mean, it's a theorem that the trajectories of your flow are on the level set of the Hamiltonian. So it's a kind of a special situation. So if you go to vector fields which are defined in the 3-dimensional space, then you can actually make this example autonomous. So it's not something which is really triggered by the time dependence, as long as you get away from some situation in which you would be too lucky. And in fact, for 2-dimensional divergence-free vector fields, there's a very nice theorem by Alberti, Bianchini, and Crippa, which tells you that you can actually go way below the regularity threshold of having like one derivative. OK, so now let me just go back to, so how do we do this? So we're still actually making a modification of deposed vector field. So I'm just going to do the same construction as before. So this is the deposed vector field, and what I do is I start from time t equals 0, and I replicate the exact same construction, but I don't go all the way up to 1. So I stop at a certain scale k, and that's why the vector field is called uk. Okay, so I go all the way to this scale. Okay, then between, say, time 1 minus 2 to the minus k and time 1 plus 2 to the minus k, I actually stay put with my vector field. And then from scale 1 plus 2 to the minus k to scale 2, so to time 2, sorry, I actually go all the way back by just simply inverting the procedure that I had before. In fact, since the procedure just it makes sense by turning squares by 90 degrees, you just see that I'm going to, so you just see that I can actually apply exactly the same vector field. So this is like, the inverse of the construction that I had before. OK, now uk converges to a function u infinity, where u infinity goes through all the scales from time 0 equal 1 by making these smaller and smaller vortices, and then actually it goes back by unwinding the vortices. And now you feed the checkerboard pattern of depot at the initial time. So what happens at the time k? Well, you have your vector field, which is like refining the checkerboard. It stops at a certain scale, then it stays put until the unmixing or inverse construction starts. And the inverse construction is simply reconstructing from the small checkerboard the old one, like the one at scale that you started with at scale 0. So you are converging now, rho 1k is converging to a solution rho 1, because in fact, the solutions rho 1k and rho 1k minus 1, they are essentially, they're exactly equal over a large chunk of time, right? So you're converging in a very nice sense. And this limiting solutions rho 1 is actually time symmetric. So if you want to understand what is rho 1 at time t and point x, you can actually look at rho 1 at time 2 minus tx. And so rho 1 gets refined and refined all the way up to converging to 0 at time t equal 1, and then the process is completely reversed, and you actually go back to the original at time t equal 2. OK, now I want to do something which looks kind of a little bit surprising at the beginning, but I'm going to give you a pretty good reason why this works. So now I'm going to do exactly the same construction, but I do the same construction on the first k scales. So I mix until step k. Now I stay put, though, for a slightly longer. So what is the upshot of this formula is that when I do the reconstruction procedure, I skip the last finer scale. So instead of exactly mirroring the pattern, I just wait a tiny bit more. And by waiting a tiny bit more in the reconstruction procedure, I'm going to claim that the demixing is completely lost. So if I do this, and I take a limit as k goes to infinity, u bar k is converging, of course, to the same vector field, because the scale which I skipped smaller and smaller in time, so it doesn't matter. But when I feed the initial data and I compute the corresponding solutions, the rho 2k are actually converging to a solution rho 2, which stays put, which does exactly the same as before from time 0 to 1. So it mixes, and then it becomes identically equal to 0. But then from time 1 to 2, it stays actually identically equal to 0. It's not doing anything. So just because I skipped one scale. So why is that possible? Well, that is possible because you have to notice the following. So when you arrive to the checkerboard ck at time 1 minus 2 to the minus k, well, rho 2k at times 1 minus 2 to the minus k minus 1 averages to 0 on each such square of the checkerboard because you got refined at the next scale, OK? So now you stay put until you have skipped, actually, that scale that you just refined. And so this averaging 0 property on those squares C, which belong to CK, are still true. And that's because I have chosen to skip the first step of the reconstruction. And this is fatal because I'm just going to tell you that when you start at the larger scale, at the larger scales, actually, the averages on those squares stays exactly the same. So let me show you why. So here's a picture, OK? So you are at the checkerboard pattern at scale, say, +1. And you skip the k step, which was refining from k to k plus 1, and which would unwind the process from k plus 1 to k. So now this means that since you have skipped the k step, the vector field which is acting is actually acting on kind of 16 cubes, right? I mean, on something which is like 4 times as big as the scale at which you are refined. So what is actually the vector field doing? Well, it's, for instance, mapping the red square into the blue square. And it's not only mapping the red square into the blue square. It does this in a measure-preserving, you can even just show that it does it isometrically, but it actually does it for sure in a measure-preserving way because it's a divergence-free vector field. So the average over the red square is equal to the average over the blue square, and the effect of the scale, which is right after the scale you skipped, is simply that it's permuting those squares, which are like twice as big as the squares at which you are constant 1 and minus 1. So then the average over the blue square and the red square actually just remains equal to 0. And of course now, if you're doing this at larger scales, it's even more so, right? I mean, at each scale, the average is actually conserved even at a smaller level. OK, so now what can you do? Well, you can do the following. You can smooth uk and u bar k with convolutions at scales which are kind of smaller than 2 to the minus k. And you produce 2 different smoothings, vk and v bar k. You see, uk and u bar k, whatever estimates you dream to have for the vector field u infinity, you have them for them too, because they are essentially just a truncation of the previous one. I mean, you've lost maybe a little bit of time regularity, which you can adjust if your vector fields were kind of, say, continuous in time. But other than that, quantitatively, you're just doing the same thing. And now you can smooth it in such a way that you keep whatever estimate you wanted to keep. For instance, you can smooth by convolution. So now, it doesn't, I mean, the initial rho is actually like piecewise constant, but it doesn't matter. You can smooth it a tiny bit, and you don't have to smooth it too much, just a tiny bit. Because if you're transporting through a smooth flow 2 different initial data, and the flow is smooth, the L1 difference, so the integral of the absolute value of the difference, is actually conserved along the flow. So if I feed rho in, I would converge either to the solution rho 1 or to the solution rho 2, which they are very different in absolute value at time t positive. And if I smooth rho in sufficiently so that, I don't know, the error that I do in the absolute value of the integral is like 1/4, when I actually look at the pattern which mixes everything and reconstructs, that one is integral 1, constant all the time. And so when I transport the smoothed version, it will have integral at least 3/4 in absolute value. But when I actually go to the one which is like, mixed and ends up to be equal to 0, well, now when I feed the smooth data, I will have to be 1/4 close in the L1 norm to 0. And that, of course, can't be also 1/4 close to the other solution, which would have integral equal to 1. OK. So of course, you could say, well, OK, so it's an interesting construction, and you can show me that I can't keep the, I can't hope for a regularization, which gives me well-postness, but which keeps the same estimates. But maybe if you give me some sort of canonical regularization, so if you regularize by convolution, you're actually able to rule out this kind of behavior. Maybe I regularize by convolution with a nice kernel, and you're converging. OK. That is the question which I've posted over there, and you can take your pick for a convolution kernel phi, and now you have a very canonical smoothing, and you can ask, OK, is it possible that rho epsilon has a unique limit? I'm not even asking whether it has to have a unique limit for all possible convolutions. I'm also just asking the very baby question. So I send epsilon to 0. Is at least the limit independent of epsilon? And here's this beautiful theorem, which was just published like this summer by Colombo, Crippa, and Sorella. So for every alpha less than 1, you can actually show that there is a divergence-free vector field C alpha. So now the divergence-free vector field is even much more regular than what I presented to you. And the answer to that is negative. So fix your convolution kernel phi. And depending on which epsilon you choose, you're actually converging to different solutions. I mean, depending on the sequence that you choose. It's kind of really a freakish example. Well, let me just say one comment about this. So this is a much, much more complicated proof. But the underlying idea is still the same, that you are constructing some funky vector field in the end, which is mixing, 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 and unmixing, unmixing, unmixing. And like depending on which, and I mean, the beauty of the construction now is that you don't have that much freedom, because you actually have to prove that depending on which scale you regularize, you're going to see either the full mixing and reconstruction, or you're going to see something which actually mixes and then stays and leaves the meat ground. So I like to think about this as a meat grinder and the meat ungrinder, right? So the procedure which goes back is the meat ungrinder. So, OK, now you can ask another very natural question, which would be natural in the literature of partial differential equation, which is like, OK, so let me add a little bit of viscosity. So let me actually keep the same vector field. And let me add a little bit of viscosity. Now, your vector field is C alpha, right? So if I'm solving the heat equation, that's super nice. Is it actually possible that when I switch the viscosity to 0, so I let epsilon go to 0, I actually converge to a unique limit? And the answer is, again, no. And it's kind of like, I mean, I'm hinting at that, but in some sense, the same ideas which gives you the first theorem actually give you even this second theorem. A parabolic regularization is not good enough either. So these are really remarkable theorems. I mean, they're truly beautiful. And as I said, they are obtained with the same underlying idea. But I mean, like, the same underlying idea when you're like looking at them from very, very far, because there's lots of very interesting new ideas in actually handling a problem which is so much stiffer than just being able, as it was in our case, to make any possible regularization, right? So we had a huge amount of freedom that they don't have. And so let me just tell you a little bit of these ideas. So first of all, they are not mixing by using like, this checkerboard pattern, because one idea that you can actually implement is that you can just simply use what are called shear flows. Like, at different times, you're going parallel in one direction, and at some other times, you're actually going parallel in the other direction to sort of mimic this vortex behavior, but without having to write like the vortex in the way we did. So somehow with flows which are in a sense much nicer, because they're kind of one-dimensional at each interval of time. There's another very smart idea, which is actually to use a super exponential scale in the various scales rather than an exponential one. And I mean, like this might give you a hint of why you might hope of getting different answers as epsilon k go to 0. Because when you have a super exponential scaling, there's going to be a lot of intermediate scales, for instance, in your convolution parameter between, say, 2 points in the sequence. So when I'm making a construction with 2 to the minus k, well, I'm convolving with something, either it's similar to the 2 to the minus k or it's similar to 2 to the minus k plus 1. But if I am actually having a sequence which is 2 to the 2 to the minus k, 2 to the minus 2 to the k, then there's a lot of scales in between in which I'm neither seeing one behavior nor the other behavior. So, and then there's actually a clever use of the Feynman-Skatz formula when you're handling the estimates for the heat equation. So it's really a very beautiful paper. Okay, so now this is the last half of my, well, less than half of my talk. So far, I just showed you sort of things which are intrinsic to the theory. I've been asked actually by some people, okay, but what about the applications of this? So there's plenty of applications of the Di-Perna-Lyons theory to several problems by Di-Perna-Lyons, famously, for instance, to the Boltzmann equation at the time. But there are applications that you wouldn't even think about. So Brouet and Semola, they actually used the estimates on regular Lagrangian flows to prove something on metric measure spaces with bounds on the Ricci curvature that, I wouldn't have made even the connection that something like that is possible by using those tools. But of course, when it comes to this type of examples in which we are trying to understand whether you can, push the theory in one direction or another direction, well, these are typically negative examples. So you might be skeptical on the fact that these ideas might be used somewhere else. So I'm going to show you an example in which you can use some of the ideas which have been generated by these constructions. So let me consider the Euler and Navier-Stokes equation. So we are on some domain of the two-dimensional or three-dimensional space. Actually, just consider omega, this domain, to be the periodic d-dimensional torus. And so the Navier-Stokes equations are a system of partial differential equations where the unknowns are two functions, so a vector field V, which is divergence-free. So you see where I'm going, right? Somehow this is a very natural problem in which the divergence-free condition is actually given to you by the equations, irrespectively of the regularity of your solution. And then there's a second unknown, which is the pressure, which is a scalar field, so the hydrodynamic pressure. And you see the equations over there. So there is the divergence-free condition, and there's the first equation, where you see the Stokes operator, which is the linear Stokes operator, which is the time derivative of V plus the gradient of the pressure, and a viscosity term, so nu times the Laplacian. And then there is this advective term. So the one in blue. So the red term, of course, if nu is positive, then you have the Navier-Stokes equation, and if nu is equal to 0, you have the Euler equations, and those are the two regimes in which we are interested. And now the advective derivative is I write it in a short form as the divergence of the matrix V tensor V, and it's equal to advecting the vector field V because through V, because V is divergence free. So there I gave you the exact formula. And of course, Laplacian of V is the Laplacian, right? So I shouldn't even tell you that. So now the Euler and the Navier-Stokes equations, they describe the motion of an incompressible fluid. And under some assumptions, so incompressibility for both of them, that is the divergence free condition. And now, in the case of Euler, the assumption is that there is no friction between nearby fluid particles. So a layer of fluid can actually slide over another layer of fluid without being slowed down by the fact that, say, the other layer of fluid is at rest. In the case of Navier-Stokes, there is friction, and there's an assumption that the friction is sort of idealized. So it is isotropic, it is actually linear, it has a linear dependence in terms of the stress tensor, and that alone even wouldn't characterize the Navier-Stokes equations. There's a little bit more to do. Okay, as I said, the unknowns are the pressure and the velocity. The velocity v is the velocity of the speed of the fluid particle, which at time t stays at point x. The pressure is kind of a force, and it's, you can think about it as a reaction of the fluid to the motion, which is due to the incompressibility. So if a certain amount of fluid is trying to enter a space in which there is already another amount of fluid, that amount of fluid actually can't be compressed, and so it's reacting to this motion, and that is expressed by the gradient of the pressure P. Okay, now, if you have a nice, honest C1 solution, or it's C1 surfaces actually, so, but you know, for making this computation, if you're not comfortable, you're taking the Laplacian of a function, maybe put 2 derivatives, but actually 1 derivative is more than enough to make sense of this. So you can scalar multiply the first equation by V, and you find this conservation law. So this conservation law is just telling you that the time derivative of the kinetic energy density, so modulus of V squared divided by 2, you can think about it as the kinetic energy of the fluid particle at the point x and t, because the density of the fluid is the same everywhere, and I can normalize it to be, say, 1. So this time derivative is equal to a flux, and the flux is due to the action of the pressure. That's why the pressure is involved in the blue term. But the flux is also due to the fact that if you're looking at the fluid region, there are some there are some particles which are escaping the region and some particles that are entering the region. And it depends on how much kinetic energy they bring out and how much kinetic energy they bring in with them. And then there is the part which is due to the viscosity, which of course has a friction effect. And somehow you see that there is one term which comes there with a negative sign. Now, if you are at nu equals 0, the red term completely drops, and that is equal to 0. And so that is actually the conservation law for the local kinetic energy. Okay, now if you integrate in space and you integrate by parts the terms which have a divergence, so the divergence term in blue drops, and the Laplacian term, which is the divergence of the gradient of that function, drops as well. So now, of course, here you have to assume something like, you know, the easiest way to think about it is that I am on the periodic torus, I don't have to worry about boundary conditions, or I might be on the whole space, and then the function has to decay in an appropriate way. And then, like, you just find that there's actually a typo because I forgot a factor 1/2 on the left-hand side. But you find that the time derivative of the kinetic energy is equal to a negative term. And the negative term is the dissipation, which is due to the friction. It's actually equal to 0 if it is Euler, if it is frictionless. But if there is friction, then it's actually strictly negative, depending on the gradient on the derivative of the function v. OK, so that's what I said. Nu equals 0, classical solutions of Euler preserve the total kinetic energy. Now, assume you actually have very small viscosity, nu, which is what in the literature of fluid dynamics is called high Reynolds number. OK, so you can look at the quantity on the left, for which I still miss a factor 1/2, as the kinetic energy, E of t. And let me call the quantity on the right-hand side Q of t. I mean, I call it Q of t, but it depends also on this parameter, which is the viscosity. So now, the Kolmogorov's theory of fully developed turbulence predicts the following. So this Q of t actually should be independent of the viscosity or of the Reynolds number if you have high Reynolds number for a typical solution. I mean, whatever this typical actually is going to mean. So more precisely, there's even a kind of precise relation between the size of Q of t and the size of the kinetic energy. And you see that in spite of the fact that nu might actually go to 0, because you are at high Reynolds number, the right-hand side, so the red term, is actually staying uniformly away from 0. Now, this is something that you believe to be true if you are at some macroscopic scale of the flow, which is fixed. I mean, because the Reynolds number is actually a quantity which depends on the viscosity and on, like, say, the length scale of the flow. So if you fix it to be equal to 1, then that is what is happening. So this is what the theory predicts. And you see immediately that if I'm going from Navier-Stokes to Euler and I send nu to 0, but that term is not going to 0, in the limit I'm not going to find a nice classical solution of Euler, typically, under these assumptions, because if I have a nice classical solution of Euler, the right-hand side is actually vanishing. Well, you should object to that. I mean, I'm skipping a theorem, which is anyway fairly robust, that if you have a reasonable solution of Euler, reasonable solutions of Navier-Stokes are converging to them. And reasonable solution of Euler means a certain amount of regularity, which is not that much. I will comment on that. And reasonable solution of Navier-Stokes means essentially solutions which satisfy the energy inequality, what are called in the literature Lie solutions. Now, if you pick up, as I hinted in my first lecture, if you pick up just distributional solution, what are called Oseen solution, then those are actually can behave in a very crazy way. This was this beautiful paper by Buckmaster and Vikol. Anyway, just assume actually you're going from smooth solution of Navier-Stokes because that is like fully decent assumption. But the limit Euler is not going to be a smooth solution because otherwise you don't have this anomalous dissipation. Okay, so there's a large literature about the theory of turbulence, both on the physical and mathematical side. But as far as I know, so what I would like to see proved, or what I would dream to prove, is that you give me a sequence of solutions to Navier-Stokes equation, which is displaying this behavior. I'm not good at probability, and anyway, if I go to the casino, I don't care that I'm winning with probability, whatever. I actually just want to win the only time that I go to the casino. So that is my approach to this. Okay, it's something that has to happen typically, but I just want to see it once. And so what do I want? I want the viscosity going to 0. I want the uniform bound on the kinetic energy for my solutions of Navier-Stokes. I want a uniform bound from below for the dissipation. But now it's tricky. I don't want actually this anomalous dissipation mechanism, so this independence of Q from, this fact that Q is bounded away from 0 to be kind of a trivial one. So what could I do? Well, I could introduce, I could just solve the Navier-Stokes equation with an initial data, which is oscillating a lot. If I put a lot of oscillation, so for instance, if I look at something like sine of kx, and I send k to infinity, there is so much oscillation in the initial data that I don't need actually the Navier-Stokes equations. Even the heat equation would actually dissipate the energy. And that's the reason is because I am oscillating so much at the level of the initial data that I'm actually converging weakly but not strongly, okay? So I want some form of control on the oscillations that I am introducing at the initial time t. At the initial time t equals 0. Okay, so that's what I said. If we introduce very wide oscillation in the initial data, even the heat equation would keep, we could keep the sequence of the L2 norm, say, equal to 1, and produce that everything is dissipated, in small time, in a new independent fashion. Okay, then as I said, if V nu k converges to a classical solution of Euler, then the dissipation rate will converge to 0. And this is actually very, very robust. By and large, if you are a Lipschitz solution of the Euler equation, this suffices. And I have a small work with Jan Brenier and Laszlo Zekai-Hidi, which essentially tells you that you can do this out of some abstract functional analysis technique if you know the right technique. Before, this was done under some more regularity assumptions with some hard estimates. You have a nice solution of Euler, and by a perturbation method, you construct a nearby solution of Navier-Stokes, and then you argue that that solution of Navier-Stokes is unique. You don't need that, actually. So that it's a very robust mechanism which doesn't need much work in terms of hard estimates and classical PDEs. Okay, so now first you could just say okay, so in the limit I'm not converging to a smooth solution of Euler. So I could just think of producing some solution of Euler which actually dissipates the kinetic energy and hope that I can approximate with a solution of Navier-Stokes. And so this, in this framework, the Onsager conjecture, which was solved by Izet, and which I mentioned in my lecture 2, might be a good candidate. So we know via these convex integration methods there are plenty of solutions of Euler which are actually dissipating the kinetic energy, and you could dream of approximating some of them by classical solutions of Navier-Stokes. However, this is certainly not going to work because Euler is time reversible, and you don't see a direction of time. So if you reverse time and you had a dissipative solution, then you have a solution which increases the kinetic energy. There's no way you're going to approximate that with a reasonable solution of Navier-Stokes for which the kinetic energy is actually going down. So that's just because there's a very simple lemma that if you have a function which is increasing, you can't approximate it with a sequence of function which is decreasing. Okay, so now, smooth solution of Euler, of course, are approximable by smooth solutions of Navier-Stokes, but then anomalous dissipation would require blow-up of Euler. So until there is a smooth solution, you can't actually have anything like that. And you need a quite severe blow-up of Euler. OK, so now here's the question. So that one is a very hard question. But what happens if I actually had a force, Fk? And now I want to add a sequence of forces which are reasonably under control. So as I didn't want to introduce oscillation with the initial data, I actually want to have these forces uniformly under control. If I have these forces uniformly under control in something like C1 alpha, then I fall into the classical framework of the solutions of Euler, and I still have the blow-up problem. But as soon as I go a little bit below, then I am in a regime in which the heat equation alone wouldn't be able to actually display this phenomenon of anomalous dissipation. And it would be interesting if Navier-Stokes does. Of course, this is a much softer problem than just like putting Fk equal to 0 and try to engineer an initial data which is doing that. OK, and I mean, you can dream of doing this in C alpha for alpha less than 1, just a little bit of less than 1 derivative. OK, that's what I said. And now here's the theorem that I wanted to tell you. So that is possible, actually. So it's possible to show that there is a sequence where the forces are under control. There is a unique solution of the Navier-Stokes for the classical forces. The energy dissipation is bounded away from 0. And as I said, the forces are under control. In fact, the solutions themselves are even like reasonably under control. They're bounded. OK, so what is, I mean, I'm just going to give you very quickly the ingredients. So there's ideas that we borrowed from the literature and some that we wrote ourselves. So first of all, there's the idea of looking at 2 + 1/2 flows. So a part of the solution depends, I mean, the solution depends only on the first 2 variables, space variables. And that means that I can break the vector field into a part which is genuinely 2D and a part which is advected. So rho k, the third component, is just completely advected. I actually called it theta k in the slide, but it should be rho k. And so the idea is to engineer a depot-like construction for the vector fields, for the 2-dimensional part of the vector field. And once I've done that, use actually the transport of what we learned for the transport equation for the part which is advected by the transport. And as I said, this is actually an idea that we borrowed from a paper by Jiong and Yoneda in a different context. So here is what is possible. So it is possible to do this, to implement this strategy. And what was surprised to us is that it really captures the borderline situation. So C1 is the well-Posner's threshold. You can't do this in C1. You can do this in C alpha. I mean, you cannot do this in a little bit better than C1. I mean, C1 probably would be kind of, borderline open situation. And you can do it for C alpha. And there are 2 important points, though. So we are still using important ideas in the literature. So first of all, we can't use depot because not smooth. We use a smooth mixer, which exists, but it's provided in a highly non-trivial paper by Alberti, Crippa, and Mazzucato in 2016. And even though, I'm just swiping under the rug a lot of problems, it seems easy to hope for dissipation because you have this kind of creation of scales. It's still non-trivial to prove it, and we actually use an idea of Drivas, Elghindi, Iyer, and Jiong in 2019. And that's all I wanted to say. So thank you for your attention.
Thank you. Any question?
So how is this theory affected if you work in a Hamiltonian setting? I mean, can you, in higher, so your examples and counterexamples in 2 dimensions,
So, OK, so the Hamiltonian setting, so if you have an autonomous vector field, then it would be Hamiltonian, and then you can actually prove much better than in the Bernoulli's theory. Yeah. If you are Hamiltonian in a higher dimensional setting, like 4D, so pretty much so it's more difficult because the condition of being divergence-free is not true anymore, but pretty much lots of the badness that I've actually showed you is still correct. So that is in particular a work of 1 year ago by Sorella and Vikram, who actually show that many of the things that you can do for divergence-free can be done. So in the luckiest dimensional situation where you can really exploit that, and autonomous, where you can really exploit that your flow becomes essentially one-dimensional, then you can prove much, much more. But as soon as you go high enough in the dimension that you still have a fully dimensional picture instead of being like ordered by the Hamiltonian, then essentially the same situation happens. Now I don't know with which amount of detail things have been proved, but I would expect that as soon as you leave two-dimensional Hamiltonian autonomous, you actually are in the same bad situation as with what I presented you.
One more question. No question? Okay, so let us thank Camillo again.
Thanks to you for staying with me.